Mr. Sebastian Stock. I want to briefly introduce him. He got his master from Leibniz University Hannover in industrial engineering, and his PhD also from the same university on nonlinear mathematical optimization and grid operation and planning. And today he is a group manager, transmission system planning and operation at Fraunhofer Institute for Energy Economics and Energy Systems Technology, IEE in Kassel. So Mr. Stock, please, the floor is yours. Oh, sorry, I have to switch on your microphone, otherwise we can't hear you. For any funny reason. Now it should work, please.
So can you hear me?
Yes, I can hear you, thank you.
Okay, perfect. And you can also see my presentation slides?
Absolutely, yeah, thanks.
Okay. So let me, okay, so yeah, hello, my name is Sebastian Stock, and I'm happy to present today our work, which have the name Robust Nonlinear Mathematical Transmission Expansion Planning based on German electricity market simulation. And this work is done together with Yannic, Denis, Mende, and Lutz, Hofmann. So the agenda for my speech, I would like to bring up the background and the motivation for this work. Then I would like to show the mathematical optimization model and the solution process which is used, and following by the optimization framework in which the model and the process is, let's say, included. And in point 4, I would like to show the simulation results for the German transmission system, and I would like to finish with a summary and an outlook for this work. So let's start with the background and the motivation. So in general, we have high requirements on electrical energy transmission, and these requirements are changing. But still the transmission grid needs to be reliable, secure, stable, and as well cost efficient. So the transmission expansion planning look for developing grid design suiting the objective security of supply, economic efficiency, and environmental compatibility. So the aim of this work here now is the development of a computation efficient transmission expansion model for using detailed grid and scenario data, and then applying this model on the full German transmission system combined with a full market simulation of 2030. On the right-hand side, you can see here that the transmission network, the German transmission network, is built out of all grids from the 4 German TSOs. And yeah, together, this is the grid model we are using. And on the top side, you can see the market simulation, which is also going then into the grid model and building out of this the scenarios. Yeah, but I will come also to some more detailed numbers to the data we used. So let's have a look on the mathematical optimization model and the solution process. So in general, you can see here the general formulation of a mathematical model. You have an objective and constraints. And yeah, we are here build up a model, which is a mixed integer nonlinear model based on DC power flow. And the expansion measures which are allowed are based on the NOVA principle used by the German TSO. So NOVA is a German abbreviation of Netzoptimierung für Verstärkung vor Ausbau, which means network optimization before reinforcement, before expansion. So this is an order you have to, let's say, met if you would like to, let's say, extend your network. So if there's an, let's say, a congestion, you can handle with an optimization measure. You have to do this first before you are more or less allowed to have more cost intensive measures like reinforcement or expansion. So I would not go into detail here into every number. So this is mainly part of the paper, but maybe one question can arise here is why is it a mixed integer nonlinear problem when it's based on the DC power flow? This is due to the fact that we have here the multiplication of variables we have into our problem. So we have the load angles out of the DC power flow, and this is multiplied with the impedances, which are in the transmission case, are also a variable. So therefore, we have here a nonlinearity into. And of course, it's also mixed integer decisions due to the fact that you, that your transmission decisions are, binary decisions you have to met. So, and this model is introduced or used in a sequential workflow of optimization. So we have a sequential decision making with this workflow, and this is also done due to the NOVA principle to map this principle. And into the steps we have on certain points we have the we have a relaxed optimization, and based on the relaxed optimization problems there are let's say the control of the decision making, and and at the end a final discrete optimization is done. Also for this, I would like to, let's say, point on the paper for the details here. So this model is then included in an optimization framework. So, and here you can see the framework on the right-hand side. Our model, which I showed, is modeled in AMPL. Then we are using as a nonlinear solver the Nitro solver. Also possible is to use the open source solver Bonmin. For our grid data and modeling of the grid, and also for the validation of the results, we are using Power Factory. Here you can also use Panda Power, which is a tool which is developed at the Fraunhofer IEE. But for this paper, we used Power Factory as a commercial tool. And the electricity market simulation is done by the scope model, which is also an IEE model. And this model provides us all the market informations we are needing. And then we have as pre-processing and control of the optimization process, we use MATLAB, and here you can also use Python. So MATLAB is combining all the data coming from Power Factory, coming from the market simulation, and build up the model preparation of the data and control the process. So between MATLAB and the optimization tool, at the end, the grid planning is, let's say, happening. So let's have a look on the simulation and the results for the German transmission system. So the grid model at the end contains 400 nodes and 3,000 branches. And all nodes and lines are geo-referenced. So every, let's say, substation or big substation you can see in Germany is geo-referenced in this model. And the electricity market simulation is a yearly simulation, and all different renewable energy sources like wind, solar, and hydro are geo-referenced in a Cosmo EU pattern over Germany. So this is on the right-hand side in the middle, the locations. So you have several cards looking like this with all the distribution of renewable energies over Germany. So this is one part of the market simulation, and of course the second one is to have for the 500 around 500 thermal power plants the let's say this decision on how they are operating in this year, and this is based on the weather year of 2011. So, and out of this, we are building for 1 year the scenarios, and for every scenario, we have to then perform the grid extension calculation, and comparing then all the decisions we are made into this year. Out of this, the final decision then is to let's say derived. So let's move further. On the link on the left side, you can see one power flow scenario. So one scenario.
Hello, Mr. Stock. We missed your audio. Sorry, you were disconnected. Mr. Stock, we can't hear you any longer. Oh, that's a pity. Can anybody confirm that this is not my problem, but can you hear Mr. Stock?
No, we
You
cannot
can't hear him either. Okay. So how could I give him a message? Can my co-chair help me?
Yes, do you want me to send him a message?
Could you please do?
Yes, of course.
I guess his microphone is broken. Obviously, he does not read the Q&A during his presentation.
I can interrupt his video if you want to.
Yes, please, because that he would notice, I guess.
Yeah.
So, can we call him? Oh, at least I see his video. Mr. Stock, we can't hear you. Can you read? Can you hear me?
Yeah, maybe now.
Yes, you're back now.
Ah, sorry.
Sorry, so the last 2 or 3 minutes have been lost, unfortunately, from your presentation. We can see your presentation, but we couldn't hear you.
Okay.
So maybe can you switch back one slide and then try to speed a little bit up?
Yeah, here on this one.
This one, yeah.
Okay, so yeah, what I said is on the left-hand side, you can see the calculation of one scenario. So for every scenario, a decision is made that there are no congestions exist in this scenario. So this is done 8,000 times. And on the right-hand side, you can then see the different decisions out of every scenario in this year. So for a branch, so let's move one further to have it a little bit bigger. So for every branch, you have this different, let's say, measures necessary over the year. So maybe, for example, for branch 101 in, let's say, around 500 time steps, line monitoring is fine, but in other time step, you have to, let's say, have a bigger measurement on this branch to meet the power flow necessities in this time frame. So, and another thing here you can see is that 101 and 100 have the same, let's say, decisions. This is due to that these two lines are parallel, but this is not explicitly modeled in the model. This came out of the let's say power flow behavior, that the decisions are made the same, more or less the same, for parallel systems. So also here 97 and 98, you can see that there is this behavior. So, and here you can see the final results on the left hand side in a geographical representation, and it also can be seen that you have the necessity of the north-south expansion in Germany due to a lot of wind you have in the north of.
Mr. Stark, you're
Yeah.
lost again.
Hallo? Hallo? Hi, hello.
Oh, yeah, you're back. You're
Yeah.
back. Okay.
Okay. Yeah, and on the right-hand side, there is the numerical representation of the results. So at the end, we have introduced, or we have one, let's say, an integral number. This is the unit gigawatt kilometers. So this is one number you can, let's say, measure what the expansion or how much expansion is applied on the network. And here we have around 3,000 gigawatt kilometer installed for this example. So now the summary and the outlook.
Could you do that in 1 minute, please?
Yeah, I will try my best.
Okay.
So you see that a robust method to solve the long-term transmission expansion planning is what was presented. Different NOVA measures can be included using decision variables in the transmission expansion optimization model. The model was applied to the full German transmission system combined with a full market simulation. And what is the outlook and further works? Of course, the implementation of further measures like expansion of DC links is necessary. This is mainly done by now. We also want to introduce operational expenditures. So to have this, we need to introduce more scenarios, so more years. So what you mentioned before, we then need to have a long time period to compare capital expenditures with operational expenditures. So this is planned. And of course, we would like to implement then for the longer time also flexible AC transmission system and further new components for the, let's say, having then the operation for this longer time period. So yeah, thank you for your attention, and I would like to be happy to answer your questions.
Yes, thank you very much. We have a few questions, and maybe since we will not probably be able to answer all the questions due to time limitations, may I ask the authors to use the Q&A in order to then answer the questions in written, so that all that is done. But I would just want to take the first speaker, which is Sergio Contreras. He's asking, why is the strategy called robust, and how are the scenarios generated?
So
on that?
Yeah, the scenarios are generated based on the market simulation I showed. And with robust here is mean that, of course, here we have an example for 1 year, but we would like to introduce more, let's say, more weather years and a longer time period. And the final decision is, let's say, made out of all the scenarios. So the grid, which is at the end, the result met the requirements in all the scenarios. So this is here mean with robust.
Okay. I've maybe one further question. In all these system planning approaches, I got the impression that Germany is being treated as an island. So there's no representation of the neighboring systems, but we have some exchange capacities in the range of 15 gigawatts to all our neighbors. So how do you deal with that? And this includes also the European trading,
Yeah, of course,
power.
of course. This is also included. Is it? It's not here on the map, let's say, shown.
Yeah.
But we started with a complete European network, and then reduce the network until we let's say see the impact on the German system is reducing. Then we are stopping, and on the grid nodes into our neighboring countries, we are, let's say, introducing the also the European results of the market simulation on these nodes. So it's it's of course it's included.
So you have a European market simulation as well.
Yes, of course, of course.
Okay, thank you very much. So there's one more question from Mr. Gupta, but I'm afraid we are running out of time. So may I ask you to answer that directly during the Q&A function?
I can do so.
Okay, thank you very much indeed.
Thanks.